Welcome to lecture 4 of module 6. In this module, we have been discussing on condensation and boiling heat transfer. First two lectures we have discussed on condensation heat transfer, and then last lecture onwards we are discussing on boiling heat transfer. Last lecture we have discussed some basic concepts, fundamentals of boiling heat transfer situations, and now in this lecture we will try to concentrate on various correlations available for boiling heat transfer, and also to see that how the boiling heat transfer can be calculated by using such correlations in different conditions. Okay. Now, to start with, what we are going to discuss is, so in this lecture we are going to discuss mostly that boiling heat transfer correlations. Now, to start with, we are going to discuss first that how a bubble of vapor remains in equilibrium, mechanical equilibrium in a liquid pool. So, if we consider that there is a liquid pool and we know that there is a bubble here, and we will assume a spherical bubble, and then here in this there will be surface tension forces. So, what happens, and this is the say diameter of this bubble. So, this is a spherical bubble of radius radius equal to r, surface tension is equal to say sigma. Okay. So, here this is the surface tension force. Now, what happens here, and this is a liquid this is a liquid pool, it is at a pressure of P L is the pressure of the liquid pool, and here P V is the pressure of the vapor. Okay. So, to know the mechanical equilibrium, we know that the pressure forces is being balanced, differential pressure forces is being balanced by the surface tension force. So, surface tension force, we know that it acts in per unit length. So, the surface tension force is 2 pi r into sigma, that is the surface tension force, assuming that it is a spherical bubble. Okay. That is assumed, and that is equal to P V minus P L. This is the pressure difference, and we know that pressure of the vapor is vapor pressure is pressure of the vapor is more than the pressure of the liquid, and this into pi into r square, that is the radius of this. This is the area on which the pressure acts, and therefore, we can say that P V minus P L, the differential pressure is balanced by this term, this is 2 sigma by r. So, this is a very standard relationship that if we know the pressure in a of the liquid, and then we know that surface tension force. If we know the radius of the bubble, then we can find out the vapor pressure, or if we know the pressure of the vapor, then we can find out the values of radius of the bubble, that we can find out. Okay. Now next, another point what we are going to discuss over here is to see that how to calculate the radius of the bubble by using some theoretical analysis. That is what we are going to discuss now, some theoretical analysis for calculation of bubble radius. So, if we do this, we will see that to start with, we will think that we will apply that Clausius-Clapeyron equation that you might have studied in thermodynamics, which is applicable between two phases. So, here we will assume that vapor phase behaves like an ideal gas, and then what we get is that according to Clausius-Clapeyron equation, d ln P pressure by dt is equal to Lv, that is the latent heat of evaporation, so is the phase change equation, and RT square. And then if we do the integration from PL to PV at two pressure conditions, d ln P, and that is equal to Lv latent heat of evaporation by R into dt by T square, and here we will write integration will be T sat, and this is equal to T L. Now, the conditions are here that T sat is, we have discussed several times, is that boiling point of liquid, T L and P L are temperature and pressure of superheated liquid, pressure of superheated liquid. As we know that to have that bubble formation, that liquid has to be little bit of superheating is needed, superheated liquid. So, T L will be higher than T sat. Okay. And then another thing is that since the vapor bubble is in thermal equilibrium with the liquid, so vapor temperature is also is taken to be T L, because the vapor is vapor in the bubble is thermal equilibrium with the liquid, surrounding liquid. And we know thermal equilibrium means the temperatures between the two phases has to be same. Vapor in bubble is in thermal equilibrium with the surrounding liquid. Otherwise, if the surrounding liquid is at lower temperature, then there will be a condensation, and then it will, the bubbles may get collapsed. Okay. So, the vapor of the temperature is T L. So, based on that, if we just do this, then we can find out from here that ln PV by PL, okay, by doing the integration, you will get Lv by R, latent heat of evaporation, by R into 1 by T sat minus 1 by T L. Now, if we do now little bit of modifications or manipulations rather. So, ln PV by PL we will write as ln 1 plus PV minus PL by PL, and that can be approximated as PV minus PL, PV minus PL by PL, and that is becoming equal to, according to the previous equation, Lv by R into T1 minus T sat by TL into T sat. Okay. Now, as we know that TL is nearly equal to T sat, so we can write that TL into T sat is nearly equal to T sat square, and then we can get that TL minus T sat, and that is equal to twice sigma is equal to TL minus T sat, okay, will be equal to PV minus PL by PL, okay, and then into R by Lv, okay. I am sorry. So, this will be equal to, if we just put over here, TL minus T sat is equal to PV minus PL by PL into R by Lv into T sat square, and we know that PV minus PL is equal to twice sigma by R. So, we will get twice sigma by R into PL, already we had, into R by Lv into T sat square. So, this is approximated as twice sigma, and this is equal to If we write again, twice sigma into r into T sat square by r into P L into L V. So, this is an equation. From this equation, if we know the definite values of say sigma, T sat and T L and all the things, we can easily calculate the value of bubble radius r. Okay. So, this relationship can be used to calculate the radius of the bubble. Now, Page has given an expression, empirical relation, has proposed an empirical relation for bubble dia, which is denoted as dB here, at detachment from the heating surface. We have to understand that the bubble is started forming already, we have discussed in the last lecture, and then it gradually grows and then finally it detaches from the surface. So, the with time the diameter of the bubble changes, size of the bubble changes. So, during the time of detachment, at the time of detachment, what happens to the diameter of the bubble, that is being calculated by the relationship given by Fritsch, and this relationship is that dB equals to CD into beta root over twice sigma G into rho L minus rho V. Okay. Here CD equals to some factor, and that is 0.0148 for water, and beta is equal to angle of contact Okay. Now, Zuber also proposed a relationship for bubble diameter, and that is F into dB equals to 1.18 tau c by tau c plus tau d into G sigma rho L minus rho V by rho L whole to the power 1 by 4, and in this case tau c is time for which the bubble is attached to the surface. So, it is basically depending upon the time it will find out the bubble diameter. Then tau d is the time that elapses before the next bubble is formed. Okay. And then F is called the frequency of bubble formation. Okay. So, this is a relation, these are the two relationships which are used, these are empirical relations to calculate the bubble diameter at different situations. Okay. Now, we will see that there are some correlations for calculating the pool boiling heat transfer. So, which is very important for us, correlations for calculating pool boiling heat transfer. Now, in this case the most important one is that we should consider is that nuclear boiling situation first. Because we already discussed, we have already discussed in the last lecture that nucleus boiling is the phenomena that we should try to work on, we should prefer. for any kind of boiling situations, because that time it is giving us the maximum very good value of heat transfer coefficient. At the same time it avoids any risk of having or reaching to boiling crisis phenomena or burnout phenomena. Okay. So, for nucleate boiling there is a very well known relationship that has been given by Rosenau relation. According to Rosenau relation, that Q dot S, that is the heat flux, equals to mu L into L V into G into rho L minus rho V by sigma whole to the power half, and CPL into T excess temperature by CSF is the constant LV into Prandtl L whole to the power n. Okay. So, this whole to the power 3. So, this is the Rosenau relation, and here the different parameters are given like this, that Q dot S is called heat flux, okay, in nucleate boiling. Okay. Then we have mu L liquid viscosity. L indicates that liquid and its unit is Pascal second. Then LV latent heat of evaporation or enthalpy of evaporation. Its unit is joule per kg. Then we have G is the gravity, acceleration due to gravity. Acceleration due to gravity, it is meter per second square. Then CPL is specific heat, liquid specific heat, it is given as joule per kg per degree centigrade. Then rho liquid density, rho L rather, liquid density, and it is definitely kg per meter cube. And this way there are some more TE excess temperature, and then we know that T is equal to TW minus T sat, and this is in degree centigrade or degree Kelvin or Kelvin. And then we have TW, we know wall temperature in Kelvin, and T sat saturation, liquid saturation temperature of liquid, okay, naturally it is in Kelvin, and say PRL liquid Prandtl number, then and it is unitless, and Q dot S is watt per meter square. So, unit of Q dot S is in watt per meter square. Okay. And then what happens is the values of CSF and N are constant, CSF and N are constants. It depends on the geometry, material of construction and the liquid material or say fluid surface. It depends on the fluid, rather liquid and surface, liquid and surface combination for boiling operation. Okay. Now, typically if we say that, say water, stainless steel, CSF and N, this is 0.01, and this is 1.0, then water, then brass, it is 0.006, 1.0, like that. Then one interesting is water, copper 0.013, and this is 1.0. Similarly, benzene and chromium it is 0.010 and it is 1.7. So, these are the typical ranges of the values. That is what I just wanted to highlight, that when we will be solving these problems, then we may have to make use of these values of these constants before applying the equations. Now, in addition to this correlation by nucleate boiling given by Rosenau, there are another useful correlation for that, which is nothing but Hb is boiling heat flux is given as 0.00341 into Pc to the power 2.3 Te to the power 2.33 Prandtl to the power 0.566, and its unit is watt per meter square per degree centigrade. And this is the boiling heat transfer, it is heat transfer coefficient, boiling heat transfer coefficient, okay. And then Pc is critical pressure in bar, Pr is reduced pressure, and T is equal to excess temperature, Tw minus Tsat, it is in degree centigrade or Kelvin. Okay. So, now in addition to this, whatever we have discussed, there is another important thing that we should know, that is called critical heat flux. So, there are certain relations we have discussed in the last lecture, that there is a critical heat flux. So, if we move more than critical heat flux, then we may, or that is the critical point where we see that, which is the more or less the metastable point, which is after which that film boiling becomes important. So, we have to be operating before this critical heat flux condition, that is the first term, the top point of the maximum of the first term in case of boiling curve, whatever we have seen. So, that critical heat flux we should find out, and our operation should be always below the critical heat flux conditions. So, to find out the critical heat flux, which is also called the maximum heat flux calculation, we have some correlations. First one is given by Linhard et al. And in 1973, here the Q dot max. So, critical heat flux, which is nothing but the maximum heat flux also we are telling, because if we go beyond that, then it can, because if we do not have the control, then it may switch over to the burnout conditions. So, Q dot max is equal to 0.149 into LV into rho V, okay, and then we have sigma, then G into rho L minus rho V, okay, by rho V square whole to the power 1 by 4, and it is in watt per meter square, okay. And the terms have significance and units, as all the terms are exactly similar to, it is same terminologies whatever used in case of Rosenau equations. So, all the terminologies and their units are as discussed in case of Rosenau equation. Rosen equation. Now, there is another relationship, that is to give the peak boiling flux. So, this critical heat flux also is called maximum heat flux, also it is called peak boiling heat flux, because that boiling happening at the peak condition. So, if I just draw again here that we had the boiling flux like this. So, this is the region, and here this is called the critical heat flux condition. So, Q dot max is the critical heat flux condition, and this is the excess temperature for that. Okay. Now, this is the boiling curve. Okay. Now, in this case, again another relationship that is given by Schön and Lenhard. Relation. According to this relation, that Q dot max is equal to Q dot max dashed, okay, then multiplied by 0.89 plus 2.27 exponential minus 3.44 root over r dashed, okay, and then here this is for r dashed greater than 0.15, and r dashed is dimensionless, radius is equal to r into g into rho L minus rho V by sigma whole to the power half, okay, and Q dot max dash is called peak heat flux on an infinite horizontal plate. And Q dot max dashed is given by 0.131 LV then root over of rho V into sigma g into rho L minus rho V whole to the power 1 by 4, and this is watt per meter square. So, this is happening about that different correlations for critical heat flux. Now, we will be discussing on some correlation on stable film boiling. In case of stable film boiling, it is also called as film pool boiling. Okay. In stable pool boiling, Brumley has given a relationship. Brumley relation can be used. It says that Hb, the boiling heat transfer coefficient, equals to 0.62. Now, Kv is the thermal conductivity of the vapor, this into rho V density into rho L minus rho V into G. Now, here is the modified latent heat or enthalpy of evaporation 0.4 Cpv into Te is the excess temperature divided by d is the diameter of the tube, and this is happening for horizontal tube, into mu V into Te whole to the power 1 by 4, and watt per meter square per degree centigrade is the heat transfer coefficient, and boiling heat transfer coefficient where suffix V implies vapor phase, okay, and d is diameter outside of tube, okay, and the equation is applicable for film boiling outside horizontal tubes, okay, and the equation can be used for, okay, but this equation also can be used for vertical plates after replacing d by L, the plate height, and the constant 0.62 by 0.70. Okay. So, this can be done, and now sometimes this is the film boiling situation. Many times we have already seen that during film boiling, because the temperature is very high, there is a possibility that radiational contribution is also quite strong. So, if radiation contribution is strong, is significant, then we can use that H is equal to that the equivalent heat transfer coefficient, and that is equal to H b, boiling heat transfer coefficient, into H b by H whole to the power 1/3 plus H r. So, H is that equivalent. So, H is the resultant heat transfer coefficient. You can understand that this is an implicit equation. So, some iterative method is required for getting a solution to this, and H r is called radiation heat transfer coefficient. H b is boiling heat transfer coefficient. This is from Brumley relation, and H r is obtained as, say, sigma S b epsilon T w to the power 4 minus T sat to the power 4 by T w minus T sat. Here sigma S b is called Stephan-Boltzmann constant. Okay. Fine. And epsilon is called emissivity of the surface. Fine. And properties are to be evaluated at Tf. Fine. And except LV at saturation temperature. This is for Brumley equation. All the parameters has to be calculated. So, this is about the correlations regarding that convective heat transfer boiling heat transfer coefficients, where we have nucleate boiling and film boiling. Now, there is another point that is called forced convection boiling. In the forced convection boiling, that we can see that it happens when a liquid is forced through a channel or a tube or over a surface, and maintained at the surface is maintained at a temperature higher than the liquid basically. Then there will be a boiling phenomena that will happen, and that vapor and the liquid, vapor bubble and the liquid, that means there will be a two-phase flow that will happen through the device or maybe over the device, and that kind of situation is called the forced convection boiling. And forced convection boiling is very important from industrial point of view, from applications point of view. A typical forced figure is being shown here regarding the forced convection boiling, if we see here that there are several regimes 1, 2, 3, 4, 5, 6, there are several regimes, 6 regimes are there in this particular case, which says that in the very first case the subcooled liquid in and there will be subcooled boiling. So, in this regime what is happening that there is that vapor is bubble is formed in this region, but this bubble cannot go to this region, it is getting collapsed. Okay. And then in this region there will be the more amount of bubbles are getting formed, and the bubbles, there is a mixture of the bubble in the liquid. So, this is called a bubbly flow. So, this flow is happening in the same direction of the flow, okay, and it is called a bubbly flow. So, and then there will be with further increase in temperature, what is happening that bubbles, some of the bubbles will coalesce and the bigger bubbles will form, and then it is kind of relationship. This is called a slug flow situation, where that it is mostly that big vapors are coming up in the form of bubbles, and then after that you can see that there is an annular region. In this annular region there will be mostly the liquid will be flowing, and in this region this is the vapor which is flowing, and then after that what is happening in this, there will be fine particles of the droplets will be there in there, and then after that here it is called mixed flow. That means all the liquids whatever is present, it will be like a small particles into this, and then finally in this region there will be no liquid, only the vapor, and they will come out. Okay. So, this what is happening in case of different regimes of flow situation in case of boiling heat transfer through a channel, and this is a typical case. We have seen that there are 6 zones, 1 to subcooled, bubbling flow, slug flow, annular flow, mist flow, single phase vapor flow. These are the 6 zones that can be observed, and of which we can very easily understand that particularly second, third, and maybe little bit of fourth, these 3 regions gives us a very good heat transfer phenomena, whereas fifth and sixth they are not at all good for any heat transfer phenomena, because it is mostly covered by the vapor. Okay. So, this is what is called forced convection boiling that takes place, and we can see that when there is a forced convection boiling, there are 2 kind of things is happening. It's one is flow of the fluid, and this flow can be a 2-phase flow kind of situation, and there is a boiling also, that the bubbles is coming into picture. So, in that case there is a recommendation that the heat transfer chain suggested. So, in case of forced convection boiling, chain suggested that the total HT, total heat transfer coefficient, can be written as HB, bubbling heat transfer coefficient, plus HC, heat transfer coefficient due to convection, due to flow. Okay. So, now this is HT is that, so that means total, this is boiling, and this is convective, that means due to flow. So, these are all heat transfer coefficients. Okay. And then a relationship is also being given, that is that for convective heat transfer coefficient, it is like because of the flow of the fluid through a tube kind of situation. In that case it will be something like Dietz-Boelter equation kind of things is used. It is like 0.023 with little modifications to that, REL to the power 0.8, okay, and then Prandtl L to the power 0.4 into KL by D whole to the power into F, and this is in watt per meter square per Kelvin. Here we can say that REL is that liquid only Reynolds number. It is defined as G, mass velocity, into 1 minus W into D by mu L. Okay. Here G is fluid mass velocity, which may have, So, it is basically kg per meter square per second, which may have the vapor component into it. So, W is called mass fraction of vapor in fluid, okay, and the subscript L stands for liquid. We know that PR is the Prandtl number, KL is the thermal conductivity of the liquid, and then D is tube inner diameter. Now, the question is KL by F, and F is a factor. We will discuss these things. F is a factor, and then HB, the relationship for HB is given as 1.218. It's a very big relation. This into KL, thermal conductivity to the power 0.79, then CPL to the power 0.45 into rho L to the power 0.49 by sigma to the power 0.5 is the 45, sorry 45, it is 0.79, sigma to the power 0.5, mu L to the power 0.29, LV to the power 0.24 and rho V to the power 0.24. So, V stands for vapor, okay, and then TE, the excess temperature to the power 0.24, and delta P saturation, okay, this to the power 0.75 into S. Now, here the delta P saturation is given as T into LV by T sat into T sat into VLV, where T we know it is TW, world temperature minus saturation temperature, VLV is VL VV minus VL, this is in meter cube per kg, that means this is specific volumes of vapor and liquid, okay, and delta P sat is it is in Newton per meter square. It is the difference of vapor pressure between the superheated liquid at TW and the saturated liquid. This is at T sat, okay, and sigma is surface tension and it is Newton per meter. And then we know that S is given as, it's a factor 1 plus 0.12 RE bar to the power 1.14 whole to the power minus 1.0 for RE bar less than 32.5, and this is equal to 1 plus 0.42 RE bar to the power 0.78 whole to the power 8 minus 1.0 for 32.5 less than RE bar less than 70, and this is equal to 0.1 for RE bar is greater than 70. So, here RE bar is again defined as 10 to the power minus 4 REL liquid Reynolds number into F to the power 1.25 F to the power 1.25, okay, and F is equal to 1.0 for 1 by xi less than 0.10, and F is equal to, this is also a factor 2.35 into 1 by xi plus 0.231 to the power 0.736 for 1 by xi greater than 0.10. Okay. And 1 by xi is equal to w by 1 minus w. I have discussed already, it is 0.9 into rho L by rho V all to the power 0.5 and mu V by mu L whole to the power 0.1, where H and F are the factors. S is called the boiling. So, S is called boiling suppression factor and F is a factor that modifies REL of liquid to Reynolds number for the mixture. Okay. Now, as we have seen that post convection, there are some more relations being given. McAdams et al. Suggested that Q dot, the heat flux, is equal to 2.253 delta T to the power 3.96 watt per meter square, where 0.2 less than P less than 0.7 megapascal. So, it is a pressure dependency. So, this is a relationship for boiling of water at low pressure, for boiling of water at low pressure, and then for higher pressure Q dot is equal to 283.2 P to the power 4 by 3 and then delta T to the power 3 watt per meter square, and here 0.7 less than P less than 14 megapascal, and delta T is the temperature difference. Delta T is Tw minus Tsat. Okay. Then another relationship for vertical tubes for forced convection boiling on vertical tube, H is equal to 2.54 delta T whole cube into e to the power P by 1.551 watt per meter square per degree centigrade, and 5 less than P less than 170 atmosphere. Okay. So, this is the relationship. Now, in addition to this, whatever we have discussed, so these are the different relationships for boiling heat transfer. In addition to this, I am going to discuss one important aspect, that is called heat pipe. So, heat pipe is a device. It is a device that makes use of a change of phase heat transfer. So, it makes use of change of phase heat transfer. So, what happens in case of heat pipe is that if you draw, it is like this. We have a pipe over here and then it is like this, okay, and then fine, and it is like this. Then what is happening is that here the heat addition at one end, takes place. So, that there is a pipe, say this is the pipe, and the pipe is being covered. So, we have a circular pipe. So, a layer of wicking material covering the inside surface of pipe. Okay. So, this is the, we can say that is the wicking material. Here this is the insulation, the heat addition. So, what is happening from there? There will be a vapor evaporation. So, vapors will move like this, and then this the vapor will be condensing. So, here you can say condensation, and here heat rejection. So, that means it is heat taken out, heat rejection. So, one end is the heat addition. So, there will be an evaporation, in another end the heat will be rejected, there will be the condensation, and that the vapor which is coming in this direction, this is the vapor flow. It will come to this end, and the heat rejection, that will be condensing, and then it will be the condensate will come into this direction, condensate. This is a condensate flow. So, condensate will come to this direction. This is a typical of a heat pipe. Okay. So, one end we are it is getting evaporated, and another end it is getting condensed and it is coming down. So, this kind of, so there will be a heat exchange. So, this is used as very commonly used for extraction of energy from hot waste gases like flue gas. Okay. And then it is used, the same energy is used to preheat some other fluid. Okay. So, this is being done using the heat pump, and many a times it can be tilted. So, one is called favorable tilt. In this case, elevation of condenser end, condensation end is higher than the evaporation end. Then what will happen? The liquid will try to come down due to gravity. So, gravity flow of condensate through the wicking materials. Okay. And adverse tilt, the opposite arrangement. The opposite arrangement is called the adverse tilt. And another thing is that the typical wicking materials used are mesh screen, SS fibers, sintered fibers, and sintered fibers, then etched micro groups and channels. So, this heat pipe is very important to us, and it is being nowadays the optimum wick design and the configuration of the heat pipe is of major research issues, and people are working in this particular area. So, heat pipe is also related to phase change phenomena. The various type of fluids can be used depending upon the temperature and other conditions. It can be ammonia, it can be liquid ammonia, methanol, water, and so on. different liquids can be used for this situation. Okay. This is all for today. We will be having some exercise for in future. We will be adding some exercise associated with it particular section in the particular module to have to calculate some problems in these particular areas. Okay. In next lecture, we will start with a new module. Thank you very much.